This one. You're given two positive integer arrays, spells and potions of length n and m respectively, where spells represents the strength of the ith spell and potions represents the strength of the jth potion. You are given an integer success. A spell and a potion pair is considered successful if the product of their strengths is at least successes. Return an integer array of pairs of length n, where pairs I is the number of potions that will form a successful pair. I'm tired. Return an integer array of pairs of length n, where pairs I is the number of potions that will form a successful pair with the ith spell. So we go through all the spells in I, and we're trying to find how many potions will do that. You could just iterate through, since are they sorted? I'm gonna assume. So this would be a lot easier if pairs was if potions was sorted. So right off the bat, let's sort. We already know what category it's in. It's a binary search. So the thing is, we could say for every spell, go through potions left to right until you find a good enough potion, and then just assume the rest would also, not assume, but work. But that means that you had to iterate through potions for every spell. We could that would be O n times m time, where n is the length of spells and m is the length of potions. Basically O n squared time, but since it's two arrays. So what we do instead is we could actually turn this into O log n log m by saying iterate through potions, by saying binary search for every spell and spells, binary search through potions, and then you'll find the right amount. Now, is there anything we can do with spells? I can't really think of anything, because it would be really hard to make a rule of like, okay, well, if spell 1 works for all these, you have to like kind of backtrack for like spell 2, because like, okay, spell 2 is stronger, so now we had to like, we could take spell 1 divided by it's too much. So here we go. For spell in spells, we're gonna say pairs equals 0 times length of spells. For spell and spells, we're going to say L equals 0, R equals let's say N, M equals length of spells and length of potions. For spell and spells, we have this pairs. We know that there's going to be an answer for every spell. So we have 0 times the length of spells. And then we're just doing a binary search. We say while L is less than M, mid equals R, L plus R, floor divided by 2. Then we'll say if why don't we make this -1? Because that way if we see a -1, we know that something's wrong. If spell times potions mid is greater So here's the thing. Are the potions unique? I don't think that they are. You can have multiple potions of the same thing. So we unfortunately can't just stop once we reach the exact success. Because you could have something like 0016 16, and let's say, I don't know, you get to like this point right here, you get to this 16, you'd assume, okay, well, all the potions to the right are greater. Well, you're forgetting about this 16 right here. So you actually wouldn't stop. Actually say if it's greater than or equal to success, then, so if it's greater than the success, then we're going to set the R is equal to mid. And we're saying mid because we're including this answer itself. So we know that mid works fine. So we don't want to remove that from the search. But what we are removing for the search is everything to the right of mid, because we know we don't have to look to there, because we know that all of those are going to be greater than success. So instead, we say L equals mid plus 1, because in that case, we can skip over mid because we know that mid doesn't work. So then, finally, once L equals M, we have mid. And once L equals M, then we should say pairs. This should probably be I in range N. Spell equals spells I. Pairs I, because that way we can get the index for the answer as well. Equals, ready for this one? Here we go. M minus L. Because once we get out of this loop, L and M are the same. So that means that we've chopped down, so everything to the right of L, actually it should be M minus L plus 1. Everything to the right of L, including L, is successful. Now, would that ever go out of bounds? I think not. I think if there's no spells that, if there's no potions that would work with this spell, then L would eventually become M. And in that case, maybe it shouldn't be plus 1. Oh yeah, it shouldn't be plus 1 because the L is a 0 index, but the M is the length, so it already accounts for that extra 1. So if L becomes M, then that means that you've iterated through the whole thing. Okay, and then we can just return pairs. I'm going to give this like a 50% chance of working. Syntax. Oh, because of the drawing I did earlier. You silly goose, Kyle. So it never ended, which means that something wrong happened. Let's try that. Oh, because L should be less than R. Wrong answer. It's always these edge cases with these binary searches. Oh. Okay, so first we have oh, because we never sort potions. That's what it was. We never actually sorted potions. We said we would, and then we didn't. Come on, just work for everything, please. Oh, thank goodness. I forgot to do the one thing I said I was going to do. You can't run a binary search on an unsorted list. That's actually crazy that it worked for any of them. I guess in that first case, potions is sorted. So, cool.